Hi folks, this is the continuation of the Unit 3 Day 1 lesson, and we're on the second video. We're going to work through an example here that should help you to kind of understand the different equations a little bit better. So this one's asking us to find the vector, parametric, and Cartesian equations of the line that goes through these 2 points. So just a reminder, the vector equation is the position vector and then plus some scalar multiple. So I'm just going to put plus t because we are going to need that, times the direction vector. So that's for the vector equation. I think that it's easier to remember this if you're trying to, if you actually understand what's happening than if you just try and memorize this formula. So to get to any point on the line, you need to get to the line. That's our position vector. Find a point on the line, find just one point, any point, and then find a direction of the line and move along that direction to any other point. So that's the scalar multiple there. So again, the position vector is get to the line. And the direction vector is move along the line. And I would much rather have you guys understand this than to try and remember like, oh, what's the R naught and what's the M and what do they mean? Just think about it in terms of I have to get myself to the line and then move along the line. So this needs to be in the same direction as the line. Okay, so my vector equation here will be R equals, my resultant equals, I need to get to the line. I have 2 points on the line and I can pick either one of those. I might pick A just because of alphabetical order. I don't know. These are not unique equations. You can get to any point on the line. You can have any scalar multiple of the direction vector and it's all fine. So plus t, now I need a vector that's in the direction of the line. So a vector in the direction of the line would be vector AB. So I'm just going to find vector AB off to the side here. So remember, subtract the endpoint minus the starting point. 2 minus -1 is 3, and -3 minus 4 is -7. So that's my move along the line vector. And then I just say that t can be any real number. So this right here, this is the vector equation. So there's my vector equation. I can pretty easily take the vector equation and write those parametric equations. That's just taking the x and y components of this equation and writing them separately. So the x component of my resultant will be -1 plus t times 3. So I'll put plus 3t. And my y component will be 4 minus 7 times t. And then I still have to write t is any real number. So I've got my vector and I've got my parametric. The last equation, which we're actually going to get from the parametric, is the Cartesian. That's also called the scalar equation. It means the exact same thing. Now, you guys know how to find the the equation of a line in that Cartesian form, because that's just our standard form, ax plus by plus c equals 0. But I'm going to show you a different way if you're given the parametric. So instead of going and finding the slope and finding the y-intercept and putting it in y equals mx plus b and changing it to standard, I'm going to start with the two pieces of the parametric equations. So I know that x equals -1 plus 3t and y equals 4 minus 7t. And what I'm going to do is solve for this t value in each of these two equations. So the first equation, just numbering them. Equation 1, I would have x plus 1 over 3 equals t. I'm just kind of skipping a step there, but I think we should mostly be okay with that. And then y minus 4 over -7 equals t. So then I have two equations that are both equal to t. I can make those equations equal to each other and just cross multiply and simplify. So I have x plus 1 over 3 equals y minus 4 over -7. And I'm going to cross multiply these. -7x minus 7 equals 3y minus 12. Bring everything to one side. -7x minus 3y. When I bring this -12 over, it's plus 12. So I get plus 5 equals 0. And just to kind of remind you, you probably saw this in grade 9, we always want to make sure that the first term is positive. So I'm just going to rewrite that as 7x plus 3y minus 5 equals 0. This way we get a unique form that everybody coming up with the Cartesian equation would have the exact same thing. Example number 2. This is asking me for the equation of a line that's perpendicular to this given line and passes through this point. It doesn't ask me for any specific form. So I think that the vector form is actually going to be the easiest to work with. So this one here, this direction vector is -3, 4. I want to find a perpendicular direction vector to that. And there's a couple different ways of thinking about this. Some people look at this very much like with geometry and thinking very visually about this, that this would be the vector -3, 4, so it would go up there. And kind of relate this back to slope and think I'm going -3 and 4, so I have a rise of 4 and a run of -3, or a rise of -4 and a run of 3. So I need a perpendicular one, and it would go out this way, and it would have a run of 4 and a rise of 3. So some people think about that and kind of very visually. Some people think about this in terms of kind of doing a negative reciprocal on the vector components themselves. And this does kind of work in R2, thinking about switching the x and y and changing the sign of one of them. And some people, again, think about this as the dot product. So you might think -3, 4 dot something needs to equal 0. So you can kind of think about it visually or algebraically, and it works either way. So if you kind of thought, I have to multiply something by -3 and something by 4 and have it equal 0, well, if they ended up the same, I could multiply this one by 4 and this one by 3, and that'll be negative and that'll be positive and that'll be 0. So whatever way you get this, you should get a direction vector of 4, 3. Or some scalar multiple. If you got -4, -3, that's fine too. Okay, and we want it to pass through the point there of -3, 5. So this is my position. This is the point on the line, and then this is my direction. This is in the direction of the line. So my line is going to be, the resultant is get to the line. That's my position on the line. -3, 5 plus t. And you can see it's not, sorry, just a bit of a sideline here. It's not always t. This one has s and says s is an element of real numbers. The parameter there could be anything. Just make sure you declare it. And then times this direction vector of 4, 3. So this is get to the line, move along the line. That's the real key there. And now we want to check, is the point 5, 11 on this line? So just as a reminder, this was -3, 5 plus t times 4, 3. We want to check, is this point xy on the line? Can you get to 5, 11 by starting at -3, 5 and going a scalar multiple of 4 and 3? So we're going to take a look at that. I find the easiest way to solve these ones is to use that parametric form. So I'm going to rewrite this vector equation as the parametric equations, because there's going to be 2. So I'll start with -3 in the x plus 4t, and my y is going to be 5 plus 3t. And still real number values for t. So basically what I'm going to do is test x equals 5, y equals 11, and I'm going to solve for t. It would need to be the same t value in each of these in order for this point to be on the line. So I'm just going to say 5 equals -3 plus 4t. Bringing the -3 over and adding, I get 8 equals 4t, so t equals 2. And then checking what scalar multiple of this would you need to find y equals 11, and it would have to be the same. So 5 plus 3t, bring the 5 over and subtract, we get 6 equals 3t, and yeah, it is on the line. So yes, this is on the line, because basically we know if t equals 2, we will get the point 5, 11. So 5, 11 equals -3, 5 plus 2 times 4, 3. So that's what that t as an element of real numbers means. It means you can put anything in there. And if we put a 2, we end up with this point we were checking. Now, if you had gotten different t values here, then there's no one number you can put in this vector equation to get the point. If you had to maybe put t equals 2 to get to the x value and t equals 3 to get to the y value, then that won't work because you're not adding that same scalar multiple in the x and the y components. So if you can put this in and find a value for that parameter, the t or the s most commonly, then you can confirm or disprove that that point would be on the line, whether or not the t was the same in each case, or if it's different in the x and the y direction, then you'd know that that point would not be on the line. And that is it for Unit 3, Day 1.